primitive man passed on his meager store of knowledge to the next generation by the slow method of example. Learning was largely imitating. The total knowledge included mainly those skills that were necessary to eke out the barest kind of existence. Among the first to add to this store of knowledge was the traveler who returned from exploring strange lands. To explain the course of his wanderings, the traveler developed crude drawings to supplement gestures and the groping beginnings of speech. Small wonder that progress was slow and that civilization dawned so gradually. We have no way of knowing how many centuries passed before the development of written language made it possible to store up and pass on the slowly growing heritage of knowledge. The printing press gave the first great impetus to the spread of learning. The printed word carried information far and wide to thousands hitherto unable to acquire it. How startling was the contribution of the telescope, which enabled man for the first time to see the relation of his world to its nearest neighbor, the moon, and to countless other planets. In an equally startling way, the microscope added another important chapter to learning by enabling man to see and study a teeming world of infinitely small creatures like these typhoid fever germs, which always had vitally affected mankind, but which hitherto had been utterly unknown. Only within the last century did the camera lens make possible the accurate, although motionless, photographic likeness, a revolutionary forward step in the ability to acquire and transmit learning. And even more recently, the silent motion picture, which overcame many limitations of time, space, and motion. Last of all, the crowning approach to reality, the sound film. The modern school can have all the effective tools of learning, and it must have them if it is to fulfill its obligation to society. This obligation is to provide educational opportunities for every boy and girl. Pupils today must learn rapidly and accurately in a complex, changing world. Courses of study present an amazing number of life experiences which must result in dynamic learning in an all too brief period of time. The ever-present walls of the classroom heretofore have shut out much of the living reality of the subjects that must be studied. How necessary, therefore, is the new teaching aid that combines all previous teaching aids and condenses them into vivid and accurate learning experiences. Let us see what extended experiments have shown as to the power of the properly made talking picture to promote learning. Note here the superior gains of pupil groups who had access to science and music films over those who did not study these films, but otherwise had identical learning opportunities. The same superiority of the sound motion picture was found by Rouland of Harvard University. His study also showed that the film-taught students retained more of their learning. ERPI's educational talking pictures are the result of a program of research and planning since 1929. This program has drawn in outstanding authorities at all levels of the educational fields and leaders in picture production techniques. As the first step in producing these classroom films, research specialists examine hundreds of courses of study to ensure that each picture topic will be integrated with existing school curriculums. Other research workers, building upon this beginning, painstakingly select materials for inclusion in units of instruction which they prepare. After these steps, Outstanding subject matter specialists are consulted. These men carefully check the authenticity and the desirability of materials that are to be included in the unit of instruction. Now, from all these materials, those elements are drawn together which can best be presented by the sound motion picture. This forms the sound film continuity. The interplay of minds continues on through the time when the final manuscript is checked against a rigid array of sound motion picture standards. Now, technical production.
Quiet. Bells.
Throughout all stages of production, every effort is made to safeguard the educational excellence of the picture. As each film is brought to completion, it is previewed by specialists in education and in film production. Only after the film undergoes this searching review, and after all necessary revisions have been made, is it approved and released for classroom use. Any teacher equipped with these talking pictures can at any time bring the secrets and wonders of the world into the classroom, however isolated or remote the classroom may be. How else could a class reconnoiter from a 5-mile height the harbor facilities of our greatest seaport and city? Or join an exploring party far below the earth's surface among the labyrinths of our great cavern wonderlands? How else then with such a film as the String Choir can all pupils study to equal advantage the cellist and his technique? Only a film like Sound Waves and Their Sources can present living patterns of invisible sound waves and show the reason for high and low tones. We see and hear that the more frequent the vibrations are, the higher is the pitch. In the study of acoustics, the talking picture uses animated drawing to show clearly how sound waves reverberate within hard surfaced walls. Now note how the sound of the voice reinforces this learning. And you hear my voice under conditions of extreme reverberation. The reflected waves pass back and forth from wall to wall many times before they are dissipated. How quickly and clearly the mechanism of the ear, sense organ of hearing, is analyzed in the film Fundamentals of Acoustics. Note first the passage from the outer ear through to the inner ear, with sound waves striking the bones of the middle ear, which transmit vibrations to the liquid-filled inner canal. In it are shown tiny hairs that receive such waves of low frequency, and here others receiving high-frequency waves for transmission along nerves to the brain. In nature, these hidden pollen tubes grow down through the stigma of the flower and fertilize the seeds inside the plant ovary. Looking even closer at one of these tiny pollen tubes, we see the marvel of protoplasm, the plant's life stream, flowing through the tube. The film plant only by microscope techniques can we enlarge the thin edge of a leaf and observe clearly the activity within. Here we see the leaf's coloring matter mixing with chemicals from the air and water from the roots to form sugar, which is plant food. We learn that the leaf is the busy food factory of the plant. In our study of butterflies, the film speeds up an extremely slow but intensely interesting action. We see here the young butterfly struggling out of its chrysalis. And now we can actually see its body shrink as the juices leave it, flowing out into the immature wings and expanding them. An action ordinarily much too slow to be observed, but amazingly clear by this device. The sound motion picture seed dispersal vividly illustrates the learning values in speech combined with time-lapse photography. This is a heron's bill seed. It has a corkscrew tail, which responds to atmospheric changes by alternately coiling and uncoiling. In this picture, we see the sharp-pointed seed actually drill its way into soil where it can germinate to advantage. How else could this be so clearly taught? In the film Plant Traps, we see this magnified view of the tiny sundew unfolding its leaves. We compare its size with that of a finger and note also the sticky surfaces of its leaves. Now it has caught an insect. We see the relentless closing in of its leaf tentacles. It is preparing leisurely to digest its victim. Stop-motion photography and voice explain several hours of this unusual action in a few seconds. Here is a dodder growing. Ordinarily, its growth movements are much too slow to be observable, but by time-lapse photography, they appear as fairly rapid twisting and turning movements. The clock tells us that we are witnessing each hour's growth within a few seconds. This could not possibly be done otherwise in the field or in the classroom. The same technique in the film Molecular Theory of Matter shows the time required for gas molecules to diffuse through the air in this cylinder. It requires about 15 minutes. But see how quickly the gas diffuses in another cylinder from which you see the air being pumped. The diffusion now is instantaneous. These scenes illustrate the value of the talking picture in presenting difficult experiments involving expensive equipment. The huge number of molecules in a cubic centimeter of a gas, here shown in size relation to a 1-cent piece, is graphically portrayed in the same film. In 1 cubic centimeter of a gas, there are as many molecules as there would be grains of sand in this huge block of sand, 1 mile long, 1 mile wide, and 1 mile high. Do we realize how railroads have developed within our country? In the film Transportation, this map shows railroads in 1830 only an experiment. In 1850, a big industry. By 1870, the continent spanned. Thereafter, a steady filling in of new areas until today all parts of our country are closely linked. A century of development graphically condensed. The film Mountain Building, moreover, condenses thousands of years of Earth processes into seconds. In this scene, we first observe buckling and warping on a vast scale. This resulted in a fracturing and squeezing, by which the famous Lewis overthrust became a considerable part of the Rocky Mountains. We see that the forces of erosion are slowly wearing down the upthrust strata, and that their harder layers are remaining. They form the present peaks. Spectacular among these lofty peaks is Chief Mountain, left standing like a sentinel far to the east of the principal ridges. In the film Geological Work of Ice, the melting action on glacier surfaces high on the crests of the Rockies is brought to the classroom, and the formation of huge ice caves may be readily and safely observed. Note the structure of the side supports, the boulders being carried along slowly by the glacier, and the stream laden with rock debris. Only the sound motion picture can rapidly and vividly summarize the many activities of the atmosphere. First, its great erosive work as it cuts away solid rock with sharp-edged sand particles. Next, its transportational work over wide areas as it scatters this sand and dust. We see its relation to the work of water as we watch rain falling. We note its significant role in the formation of soil, the ultimate support of all life. We learn that without the atmosphere, the Earth would wheel eternally along its orbit like the moon, baked by day and frozen by night, a barren, lifeless, uneroded sphere. The moon and other planets can be studied to best advantage by telescopic views adapted to the classroom screen and accompanied by lecture interpretation. By these techniques, the moon's lifeless craters can be quickly contrasted to our own Earth's rumbling infernos. It is only with the aid of this marvelous medium of communication, the talking picture scientifically prepared for classroom use, that the world and its neighbors, under the skilled guidance of the teacher, can become the laboratory of the classroom. This teacher believes that planning is essential for the development of worthwhile classroom activities. She is here preparing to guide her pupils in the study of plants. She selects from the local film library the sound motion picture Plant Growth because it will meet the interests which have been expressed by her pupils. The teacher is aided in her planning by suggestions found in the teacher's manual which accompanies the film. In a preview of the film, she finds connecting links with pupil interests which grew out of a unit previously studied. These will form a background for the initial film showing.
You remember in our study of bees, we learned how insect life and plant growth are closely related. We were curious then to know how the bees carried pollen from one flower to another, the kind of flowers bees visit, and the conditions under which a seed grows into a plant. Now let us see how the film Plant Growth answers these questions. You'll probably find other questions you want to raise after you see the film.
It visits. After the pollen has fertilized the flower withers and the pod grows to accommodate the growing seeds within.
But how do seeds start to grow? Are all seeds spread like the ones we saw?
Well, let's try to find out. Let's bring into class tomorrow as many different seeds as we can and find out how they are carried. I saw one this morning that had wings. Yes, Harry?
How long will seeds live if they're not planted? In the film, we saw the young plants die on the rock. But I know a place where plants grow on rocks.
Yes, but do you remember what the film said the plant needed in order to grow?
Why can't we plant some seeds in our rooms and see for ourselves what they need?
We have a cactus plant at home. What kind of seeds does it have?
Now that's a good question, Jack. And here's another. In what kind of country are cactus plants usually found? That leads us into a very interesting study. How plants are adapted to the place where they grow.
Here is a physics class well along in their study of sound. They have already seen the film Sound Waves and Their Sources. This group is experimenting with harmonics. This one is studying sound wave frequencies. These pupils find that sound does not carry through vacuum.
Mr. Roberts, does this mean that if there were no air, we would never hear any sound?
The first time we saw the picture, we learned about the sources of sound and how the waves are started. But since then, the class has asked many questions similar to yours. Perhaps this would be a good time to study the film again and see the answer to some of our questions. What causes sound waves to travel?
Sound wave impulses are carried by air molecules. The air is compressed as the prongs of the fork spread out. As they spring back, a partial vacuum is formed. This results in outward moving condensations and rarefactions.
What type of sound source is the voice?
In the trachea and in the cavities of nose, mouth, and head are elastic columns of air which can be made to vibrate. The vibrating source is in the voice box and consists of two muscular strips called the vocal cords.
Why does music sometimes sound louder over water at night?
The portions of sound waves near the surface travel more slowly through the cooler air near the water. Their upper portions that would normally be unheard are bent down toward the surface, and the wave is thus focused and strengthened.
The richness of this direct teaching has led many of the pupils to explore unusual bypaths.
In the clarinet, the sound is caused by a vibrating column of air which becomes shorter when the player takes his fingers off these holes. Thus, the tone becomes higher, like this.
Other members of the class have measured distance by sound waves. Still others have charted how sound is recorded. And others have surveyed the acoustics of the school auditorium. Here is a general science class finishing a study of erosion. The pupils have seen the film Work of Rivers several times, each time for a specific purpose. Note the teacher's technique in taking advantage of the film's possibilities for the purpose of review.
Let's see the film again today to review what we have learned in our study of erosion. Perhaps some of you should pay special attention to the part of the film which shows how rivers are formed. After you've seen the film, I should like to have each of you write a summary of the most important ideas we've covered.
Today, as through long ages past, tremendous forces are at work tending to reduce all land to sea level. Were it not for great opposing forces, rivers would long since have brought all land to the level of the sea.
Here, the teacher turns off the sound of the film, and pupils describe scenes which the class has been studying.
This tiger eats raw meat. He misses his house his home in the jungle. His stripes would make him hard to see in the tall grass. This caterpillar is spinning a strap. He keeps adding a strand of silk to it every time he moves his head across. This strap will help to hold him to the branch after he turns into a pupa.
This shows how lightning happens. The top part of this cloud has negative electricity and the bottom positive. The wind blows the top part off, leaving a strong positive charge just above the earth. By induction, the earth underneath becomes negative. When this charge gets strong enough, a great spark jumps across. This is lightning.
You remember when we studied oxidation and reduction last term? The film explained the chemical action of reducing agents on oxides. This week, in our study of metals, we plan to investigate the general topic of reducing ores to their metals. Let's review the film again to make sure we understand the general basic principles of reduction.
In this cross-section drawing, we see the furnace being filled with alternate layers, one of ore and limestone, another of coke. A hot blast rushing up from the bottom of the furnace converts the coke into the gas, carbon monoxide. This removes the oxygen from the iron ore, reducing it to metallic iron. The continued intense heat melts the iron, which passes through to the bottom of the furnace and is drained off.
These classroom scenes have illustrated first the planning of the film lesson, including a careful study of the film to be used. Next, the way the teacher may introduce the film showing. And third, how the teacher may guide the discussion after each showing. This film has shown how the sound motion picture may be used to initiate the unit, to assist the teacher in direct instruction, and to serve as a quick and accurate review. The many effective ways in which the educational sound film is being used suggest that the dynamic quality of this new medium in bringing a wide range of life experiences to the classroom, its authentic and concise presentation by which it overcomes limitations of time and distance, and the facility with which it presents materials otherwise impossible to study, constitute